Europa, Jupiter's second moon. We absolutely must get there. While everyone looks toward the dusty plains of Mars, imagining geodesic domes and rovers racing among red rocks, there's an icy world in Jupiter's orbit that could prove to be the true gem of the solar system. A world where beneath an ice crust hides more water than exists in all Earth's oceans combined. A planetary aquarium that could host more life than we've ever dared to dream. Which moon are we talking about? Well, who doesn't remember 2001: A Space Odyssey by Arthur C. Clarke, where the enigmatic monolith left a disturbing message to us Earthlings. All these worlds are yours, except Europa. Attempt no landing there. Well, maybe it's time to disobey that mysterious warning. What do you think? Try to give yourselves an answer after watching this spectacular video. A tiny point of light. That's what Europa was for almost 4 centuries. A minuscule light source, weak as a 6th magnitude star. Nothing more than the second moon in order of distance from Jupiter, and the smallest of the 4 discovered by Galileo in January of 1610. By the end of the 19th century, scientists managed to estimate a diameter of about 3,100 kilometers or 1,926 miles, comparable to our moon. It was therefore reasonable to think it was a very similar body, arid and heavily cratered. It was only in the 1960s, thanks to the first spectroscopic studies, that they began to suspect its surface was instead covered with ice. Then the definitive word went to interplanetary probes and the first missions to the outer planets of the solar system. It was Voyager 1 in March of 1979 that photographed the Galilean satellites up close for the first time, particularly Io, Ganymede, and Callisto, while Europa, more distant during the probe's flyby, had to wait for Voyager 2's arrival in July of 1979. And the first high-resolution images of Europa showed ice plains crossed by thousands of dark streaks that overlapped like a gigantic reddish network spread across the entire surface. But immediately something even more extraordinary was noticed: the almost complete absence of impact craters. Some were detected, but not in the numbers you'd expect from a planet with little or no atmosphere. In their place, instead, only those long scars, which sometimes abruptly interrupted, indicating that at that point, the surface had somehow torn, bringing darker material up from the depths. At this point, the questions of crucial importance had become at least 3. 1. Why were so few impact craters visible? 2. Why was the surface cracking in that way? 3. What was emerging from the planet's interior? Needless to say, all 3 questions would have to be solved together. Since it's scientifically completely unreasonable to believe that Europa shows few impact craters just by lucky chance, there was only one other hypothesis that could be advanced to explain the phenomena, namely that the planetary surface had been remodeled over time by particular geological events. In other words, the satellite had to still be geologically active, which meant that inside Europa, there had to be a permanent heat source. The first clues in favor of this hypothesis came from considering the so-called Laplace resonance, a particular gravitational interaction phenomenon between Jupiter, Io, Europa, and Ganymede. In practice, the orbital periods of these satellites are integer multiples of each other. This means that every time Ganymede completes one orbit around Jupiter, 7.2 Earth days, Europa makes 2, 3.6 Earth days, and Io makes 4, 1.8 Earth days. This particular way of orbiting Jupiter causes gravitational perturbations that, by periodically stretching the satellite in all directions, translate into tidal effects that produce heat and mechanical effects of enormous proportions. This, for example, is the same cause of Io's intense volcanic activity, but it's been calculated that Europa's interior could also be so hot as to melt ice below the surface already beyond 10 kilometers, or 6.2 miles in depth. So it was that, although it might seem a crazy idea, astronomers began seriously thinking that beneath Europa's icy crust, there could really be hiding a great liquid ocean. The Galileo probe confirmed this, which, starting in December of 1995, had flown over Europa a dozen times, taking thousands of extraordinary photos, and had especially measured gravitational values in the layers immediately beneath the icy mantle, compatible with a density similar to that of water. Salt water, more precisely. A real ocean, about 100 kilometers or 62 miles deep, and with a volume at least double that of all Earth's oceans combined. But can all this, which anyway isn't little, really make Europa an alternative to Mars and Venus regarding colonization? Mars, for example, is much closer than Europa, 55 million kilometers or 34 million miles its minimum distance, versus Europa's 630 million kilometers or 391 million miles, has seasons, 24-hour days, and that reassuring similarity to Earth's deserts that make us feel at home. But then, looking closely, regarding resources, the comparison is merciless. Mars offers you rocks, dust, and some water if you're lucky. Europa offers you a boundless ocean, pure ice for drinking water, and the possibility of extracting oxygen and hydrogen from water through electrolysis, not counting the minerals dissolved in the ocean and possible salt deposits on the surface. Hey guys, just a moment before we continue. Don't forget to subscribe to our channel, clicking on the notification bell, and give us a thumbs up so you don't miss out on our daily videos. Obviously, not everything is roses in this aquatic paradise. Europa presents challenges that would make even the most daring space engineers pale. First of all, lethal radiation. Jupiter is a radioactive giant, and its magnetic field traps charged particles, creating radiation belts that would make Chernobyl seem like a health spa. An unprotected human on Europa's surface would receive a lethal dose of radiation in a few hours. It would be like living inside a particle accelerator while someone shoots neutrons at you full time. And then there's the prohibitive distance. Europa is between 628 and 928 million kilometers, 390 to 577 million miles away from us, depending on orbital positions. A journey would require between 3 and 6 years with current technology. No quick weekend trips. No possibility of returning home if things go wrong. Anyone leaving for Europa must be ready to stay there for decades, maybe forever. But perhaps the most incredible challenge is the icy crust. To reach the ocean, you need to drill through 15 to 25 kilometers or 9 to 16 miles of extremely hard ice. It's like digging through Earth's entire crust, but with ice harder than concrete at temperatures of minus 180 degrees Celsius or minus 292 degrees Fahrenheit. Every meter would be a battle against an environment that doesn't want to be violated. Europa's ice isn't the soft stuff you find in your home freezer. It's crystalline ice, compressed by millions of years of pressure, hard as granite but transparent as glass. The drillers would have to face not only the hardness of the material, but also the refreezing problem. While you dig, the ice behind you tends to reclose, sealing the tunnel. It's a race against time and physics itself. And then there are the extreme conditions. No breathable atmosphere, extreme polar temperatures, gravity reduced to only 13% of Earth's, and an environment where the word hospitable doesn't even exist in the vocabulary. Plus, how could we transport a team of 5 or 6 technicians and scientists to Jupiter's orbit, which on average is 2,000 times farther from Earth than the Moon, the only celestial body we've ever set foot on, in acceptable time, get them down to Europa, give them a way to build a base with accommodations and laboratories, ensure them food supplies sufficient for years, and equip them with machines to generate energy and instruments for research? Thinking we can do all this starting from Earth with a direct journey without using intermediate colonization stages, Moon, Mars, asteroids, presupposes having available a capsule powered by nuclear propulsion engines and not chemical or ionic ones like today's, capable of getting astronauts to their destination in 6 months maximum. Not to mention that the crewed mission should be preceded by an automatic mission capable of putting a rover on the surface to ensure that minimum conditions for survival actually exist. Having the foresight to establish themselves near a geyser, however, the colonists would have at their disposal a continuous source of water, which could also be used to obtain breathable oxygen through electrolysis, heat, and energy. Moreover, to ascertain the presence or absence of life, researchers would have the possibility of analyzing water brought to the surface by the geyser without needing to drill through ice to reach the salt ocean. But all this, we repeat, would be tackled in short times, only if the motivational drive were reinforced by the certainty of going to study, for the first time, an alien life form. Lacking such motivations, we don't believe it possible that an expedition of this type could be organized before 100 or 200 years from now if the purposes were generically exploratory or directed toward searching for raw materials unfindable on Earth. To put it briefly, compared to other potential colonization sites, the Jovian system is very far from Earth. As such, transporting crews and all the heavy equipment necessary to build a colony would require a lot of time, as would missions where resources are transported to and from the Jovian moons. Consequently, colonial ships would have to be much larger and heavier, and would require advanced propulsion systems to ensure they make the journey in a reasonable time frame. Missions to and from the Jovian moons would also require bases between Earth and Jupiter to provide refueling and reduce the cost of individual missions. This would mean that permanent outposts should be established on the Moon, on Mars, and most likely in the asteroid belt before any mission to Jupiter's moons could be considered feasible or convenient. This will obviously happen, and the day will come when we'll establish ourselves on Europa too, but this won't happen according to our predictions before the year 2150. Always provided that, as we've explained and as we hope, the discovery of life factor doesn't intervene to accelerate everything. For now, NASA and ESA are developing increasingly ambitious missions toward Europa. The Jupiter-Europa Clipper, launched in 2024, will study the icy moon in unprecedented detail starting in 2030. According to a timeline under study by NASA, in the 2050 to 2070 years, automated missions will drill through ice and release mini submarines into the ocean for seafloor mapping, life research, and chemical composition analysis. These drillers, or cryobots, will use miniature nuclear reactors to melt ice in front of them, while advanced thermal control systems will prevent tunnel refreezing. Between 2070 and 2100, underwater habitats will then be installed for crews of 6 to 10 people, capable of withstanding oceanic pressure and providing livable environments for months. This means self-sufficient environments, with air and water recycling systems more advanced than those of the International Space Station, hydroponic gardens that exploit Europa's abundant water, research laboratories where to study never-before-seen life forms. Compact nuclear generators would provide constant energy in a world where the sun is just a distant speck. Finally, between 2100 and 2200, the first permanent settlements could be born. Self-sufficient underwater cities with hundreds of inhabitants, extractive industries that exploit oceanic resources, research centers for astrobiology, and perhaps the most important discovery in human history. Sure, the comparison with Mars has its problematic aspects. Travel time is brutal, 3 to 6 years versus 6 to 9 months for Mars. Communications with Earth would require 35 to 52 minutes for one-way communications, or 70 to 104 minutes for bidirectional conversation, making real-time remote control impossible. Every decision would have to be autonomous, every error potentially fatal without possibility of external help. Maintaining an underwater habitat on Europa would be incredibly complex. Every component would have to be designed to last decades without intervention, every repair an extreme engineering operation. And then there's the psychological factor, perhaps the most difficult to quantify. Living in a permanent underwater environment, never seeing the sun or breathing natural air, surrounded by a dark and boundless alien ocean, would require unprecedented mental preparation. The first Europa colonist would have to be not only technically competent, but psychologically stronger than any explorer in human history.